the free energy, basically to show that what we did last time in dimension 1 and 2 is not very sharp, not very far to be sharp. And the proof will be only complete in dimension 2, and I will explain why. In dimension 1, okay, some element of the proof still go through, and it kind of give indication of why beta to the 4 is the right order of magnitude. Okay, and yeah, because yeah, it's always better to present the simplest possible proof. I will work in the case of bounded environment. Okay. So, theorem f beta is larger than minus exponential minus c divided by beta square. So there exists c positive such that for all beta in 0, 1, okay, this is true. Okay, and you can think of this c as large. Okay. Okay, and yes, I think I already told you the optimal value for c is 1 over pi, but this is not what. Okay, you can pretty much see from the proof where it's coming from, but we are not going to prove this. Okay, so well, for lower bound, okay, yeah, remember for when we were trying to go with upper bound, I was telling you that. Well, we had a quantity which was yeah, subadditive, and it would have been better if it was superadditive. Or the contrary, maybe? Yeah, no. That was superadditive, and we wanted it to be subadditive. So in this case, things goes in the right direction, right? We have that f beta is equal to the infimum over n, 1 over n, e log wn. Okay, so you just need to find a bound on this for 1n, and this will be good. Okay, so let me write what we are going to prove. So if you want, I think that's a lemma. We are going to prove that, okay, there exists C positive such that E log Wn is larger than minus log 2 minus C beta log 4 E Wn square. And there is an n here, and there is a square root here. Okay, so okay, why is this important? Okay, we will see. You will see. This is kind of convenient, but we are still we have a bit of a problem because we don't know how to compute this. Okay, and if you use Jensen, basically you're going to have things in the wrong direction. So what we are going to do instead is to say, okay, we don't know how to compute this, but what we can do is have a bound on, say, the median of this. Okay, not the mean, the median. Because, well, we can bound moments of this, and then use techniques to get some information on the median. And if we have information on the median, then we are pretty much done because we have concentration. So if you have concentration around the mean, we also have concentration around the median. So it means that the median and the mean cannot be too far off. Okay, so this is where this square root of n come from. Okay, because we have concentration of the scale on the scale square root of n. Okay, so yeah, the idea is, okay, so I'm going to prove this. I'm going to show how you derive this by concentration, and then we are going to compute the second moment, and to show that, well, if you take, so here, the idea is that you are going to take n of order, well, n equal exponential c over beta 2. Okay, for some large c. We are going to plug this in there. Okay, and what you will get is basically that, well, f beta is larger than minus 1 over square root of n. Okay, we want this to be of constant order. Okay, is the strategy clear?
We have already explored this question, the expectation of WNs.
Yes, 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 yes. I'm going to use the formula we already have. What we haven't explored is really, yeah, we have explored basically. We have said, okay, in dimension 3, it's finite when beta is small. Okay, now we are going to ask a different question. Is basically, well, when in dimension 1 and 2 we know that it explodes when n grows, and we want to know when it starts to explode. Okay, if beta is small, what's the largest n you can take so that this is smaller than 2? Okay, this is 2 is arbitrary, but just okay. Any other question? Okay, so yeah, let me recall the concentration inequality that we are going to use. So yeah, okay, let me also assume here that E of omega 1, 0 is equal to 0. Well, this changes nothing, okay? And I will also assume that this is equal to 1, and this is just a rescaling of beta. Okay. So yeah, what do we have? So reminder. The probability that log Wn minus E log Wn. So the probability that you have a deviation from above here. Okay, we have shown that this was smaller than exponential minus a constant times u over n squared times beta squared. Okay, this constant here was dependent on the bound you have on absolute value of omega. Okay, and there is no square here. Okay. So yeah, what do we get from this? We get that in particular. Okay, so let's take a particular value for u. So let's take basically u plus this to be equal to log 2. Okay, so what can we say about the probabilities that Wn is larger than 1/2? Well, this has to be smaller than exponential. So okay, this is for u positive. Okay? So here I'm kind of, okay, so I'm assuming that E log Wn is smaller than minus log 2. Okay, so this is an upper deviation from the mean. Okay, if this is not true, then this is true. So there is nothing to prove. Okay, so here I'm not assuming anything. Okay, and here we get exponential minus, okay, C log 2 plus E log Wn square over n beta square. Yes. Okay, so now I can, remember I want a bound on this. Okay, so I'm just using this thing. I'm just a bit worried about, yeah, okay, this thing is going to be, okay, what's the value of u here? Yes, okay. Yeah, here's this thing, it's not u, it's minus u, but there is a square. Okay, so don't really worry. Okay, so what we have is that E log Wn plus log 2 square is smaller than n beta square. Okay, over C, perhaps. Okay, yeah, perhaps small c because. And then you have log 1 p Wn larger than 1/2. Okay, so in other words, this gives you that log Wn, the expectation of this. Okay, I'm taking the square root here, but I don't forget that this is negative. So this means that, okay, this thing is larger than minus the square root of this. Okay, so this gives me minus log 2. Okay, and I get minus, okay, c prime beta square root of n log 1 over the probability that Wn is larger than 1/2. Okay, so to conclude, the only thing I have to show is that this is smaller than 4 times the expectation of Wn square. Okay, and for this I'm going to use, no, nobody knows? Sorry? Okay, so yeah, kind of. Well, in fact, it's okay. So you have Markov. When Markov doesn't work, you use Chebyshev, and when Chebyshev doesn't work, you use Paley-Zygmund. So this is Paley-Zygmund inequality. And I don't know. I never saw it in any basic probability class, but it turns out to be very, very useful. So what does Paley-Zygmund inequality tells you? Well, it tells you that if z is non-negative, it's a random variable, and e z is equal to 1, then, okay, and theta belongs to 0, 1, then the probability that z is larger than theta, okay, so this is the probability that a variable is at least equal to theta times its mean, okay? Well, it's larger than 1 minus theta square 1 over e z square. Okay, so then you apply it to theta equal 1/2, and you get that this thing, okay, is smaller than 4 wn squared. Okay, and the proof of this is quite elementary. So you start with 1. So 1 is the expectation of z. Okay. Then it's smaller than the expectation of z times the indicator that z is larger than theta. Well, plus the expectation, okay, yeah, here you can, I think you can put strict here, okay. It's useful, okay, you can use it for theta equals 0. Okay, I mean, it doesn't change anything. And then you have the expectation of the same thing on the complementary event, but this you can bound it by theta. Okay, and so then you have that 1 minus theta is smaller than this. And then you use Cauchy-Schwarz. And this is strictly larger, sorry. Okay, so very useful, and basically, yeah, like if you have something with mean 1 and you try to use Chebyshev, things will kind of fail as soon as your variance goes beyond a certain threshold, perhaps, I don't know, 1. Or, I mean, like if you try to show that things are positive with a certain probability. Yeah, this gives you a result even when this is really large. So this turns out to be useful. Okay, and if you want, okay, I don't know if it has a name, but you can use a variant of this using Hölder instead of Cauchy-Schwarz. Okay, if you just have a moment of order larger than 1, you still get a result. Okay, so okay, basically now to conclude, we need to compute this. We need to compute this. Okay, and basically we need to show, well, if we take this with C sufficiently large, basically this C and this C are different. Okay, if we take this with C sufficiently large, then this thing is smaller than 2. Okay, and then okay, you have log 8 and okay. So yeah, let's go back to our computation of the second moment. So if you remember, the expectation of Wn square, I mean, you can compute just by using Fubini. Okay, and what we obtained out of this was equal to exponential sum from n equal 1 to n time, okay. This is the expectation with respect to two independent random walk. And what you get is basically the Laplace transform of, okay, so you get exponential lambda 2 beta minus 2 lambda beta. Okay, this exponential here is just the second moment of exponential beta omega minus lambda beta. And then you get the sum from n equal 1 to n, the indicator that xn1 equal to xn2. Okay, and we want to bound this. So yeah, I'm going to, okay, equal. I'm going to say, well, this is equal to the product from n equal 1 to n of 1 plus chi beta indicator xn1 equal xn2. Okay, and what's chi beta? Well, chi beta is just exponential lambda 2 beta minus lambda 2 lambda beta minus 1. Okay, the minus 1 is not in the exponent. Okay, so if you want 1 plus chi beta is just this exponential. Okay, and what I'm saying is that, I mean, I'm just saying this sum here, it's a product. Okay, and then the exponential, I'm saying, okay, it's equal to 1 when I don't have, when the indicator is equal to 0, and it's equal to 1 plus chi beta when the indicator is equal to 1. Okay, so, yeah, so why is this convenient? Well, you will see it in a moment, but the idea is that this is a product, we can expand it, and then when you expand it, okay, you have a product of indicators, you get basically the probability of something. And this is a probability for which you know the asymptotic. Okay, so this turned out to be convenient. Okay. So what's important here is to compute the asymptotic of chi beta. So let's look at lambda beta. So lambda beta, it's well, the expectation of the log of the expectation of exponential beta omega 1, 0. Okay, so because of this, well, if you look at lambda prime beta, well, it's just omega 1. It's just the expectation of this. Just applying and if you look at the second derivative, well, it's just okay, I'm just taking the derivative of this. So I get the expectation of W1, 0 square exponential beta 1, 0 minus, and okay, when I'm taking the derivative here, I get exactly the same thing. So what I get here is expectation 1, 0 beta omega 1, 0. Square, and here I get this. Okay, here I'm doing nothing more than applying standard rule for derivation, differentiation. And okay, so the important thing to note here is that, okay, basically when beta is equal to 0 here, okay, what I get here is the mean of omega 1, 0, and here it's the variance of omega 1, 0. Okay, so because of my assumptions, I have that lambda prime 0 is equal to 0, and lambda prime of 0 is equal to 1. Okay, and okay, somehow expectation variance, they have also, you have extension of this to higher order, okay? So I think the third thing might be the kurtosis, and I think probably after that they don't have names. But basically, the derivatives of this log Laplace transform at 0, these are things that are called the cumulants, and sometimes they are useful for. Okay. So the cumulants, they are basically like recentered versions of moments. Okay. Okay, so the good thing is that here we know that, well, lambda beta is equivalent when beta goes to 0 plus 2 beta squared over 2. And thus lambda 2 beta minus 2 lambda beta is equivalent when beta goes to 0 plus 2 beta square, and therefore chi beta is equivalent when beta goes to 0 plus 2 beta square. Okay, just because it's the exponential of this minus 1. Okay. Okay, so now that I know how this thing behaves, I'm going to make this expansion and to see how we can estimate this. Okay. So I'm going just to use well, standard binomial expansion, multinomial expansion. So I'm saying that this thing is, well, the sum over I included in 1n of psi beta to the power I and times the probability that for all n in I, xn1 is equal to xn2. Okay? I mean, here I'm just expanding. Each time I'm expanding, basically each term corresponds to a subset of my set of indices for which I choose this term. Okay? And then instead of writing the expectation, I put directly things there to have the expectation of the product of indices. And the product of this indicator function is the indicator of the intersection. So I get this. Okay. And okay, if you want, one way to rewrite this is well, to say that this is the sum from k equals 0. Well, if you want to n, I could put 0 or n or infinity. Okay, then I have the sum over 0 less than n1 less than n2 less than nk less than n. Okay, this is increasing enumeration of my set I. Okay, and then I have the product from I equal 1 to k. And then I have the probability that for all I in 1k, x and I1 is equal to x and I2. Okay, but now, okay, the reason why it's convenient to write it this way is that this, no, okay, I went ahead. The reason why it's convenient to write it this way is that this thing can be factorized. Okay, basically, if you go to the penultimate intersection, okay, what you see ahead are two independent random walks, okay, with a fixed starting point. So if you condition to that starting point, okay, well, these things are two independent random walks starting from the same point. Okay, and here the starting point doesn't really matter to know where the next intersection is. Okay, so okay, no, okay, it's better to see this way. You look at yn, which is okay, yeah, yni is equal to 0. Okay, where yn is equal to xm1 minus xm2. Okay. So this is a random walk. You can use a Markov property for it, and therefore, this thing, okay, you can just factorize it. So this thing here is just the product from I equal 1 to k of the probability that y n I minus n I minus 1 equal to 0. Yeah. Chi beta to the power k. Okay, you see that you have the first term is just equal to 1 here. Okay, when you have the and after some point also, when k is larger than n, all the terms are equal to 0 because this sum is over an empty set. Okay, so okay, we are going to use a few things. So yeah, we are going to use that chi beta is smaller than 2 beta square. Okay, just beta is small. And here, okay, I want to factorize this sum. So what I'm going to do is to set mi equal to ni minus ni minus 1. Okay, now what kind of prevents me from factorizing is that, well, the range of the mi is not product. But I can make it product. I can extend the range. So I will take mi belongs to 1n. Okay, instead of sum of the mi smaller than n. Okay, so clearly this is an extension of the range, so I get an inequality that goes in the right direction. Okay, so using this, I get the following. I think I can put this there. so this is smaller, well, than the sum from k equals 0 to infinity, and then I get 2 beta square, and then I get the sum from m equal 1 to n, the probability that yn is equal to 0, and I get all of this to the power m. Okay, so therefore, if I want to know when my second moment explodes, I just have to worry about, well, when these things get, say, larger than 1. Okay? Okay, let's say we want this to be smaller than 2, then we just want this thing to be smaller than 1/2. Okay. So, well, we can look at this in any dimension. So let's do it in dimension 1 and 2 simultaneously. So what we have is that just using the local central limit theorem, this thing, it's smaller than some constant divided by n to the d over 2. Okay? So therefore, when d is equal to 1, the sum from n equal 1 to n of p yn equals 0, well, this is smaller than some other constant times square root of n. And when d is equal to 2, the same thing. It's smaller than the constant times log n. Okay, so basically what this gives us is that EWN square is smaller than 2 if beta, if n is smaller than, say, delta times beta to the 4, if d equal 1. Okay, I mean, basically, beta to the minus 4, sorry. Okay, I have a square root of n. So this beta to the minus 4 is going to give me beta to the minus 2, which is going to cancel this. So I just need some delta to cancel this constant and this factor 2. Okay, so I guess, yeah, I can make even me something like 16c, okay, where the c is just the same as here. Okay, so it doesn't give us some right bound for the free energy, okay, because of this square root of n here is not really good. You really would like to have, well, maybe no beta and no square root of n here. Just saying when the variance is finite, basically this thing should be of order 1. Okay, perhaps our concentration result in this situation is not optimal. Okay, so but therefore it kind of indicates why the free energy is of order beta to the 4. Okay, in dimension 1. But if you plug it in there, you get beta to the 3, which is not good. Okay, and if n is smaller than exponential minus, and yeah, so this is a C2, and what do we get? We get this log n. We want this log n to, so minus I'm just trying to put the constants at the right places. Yes. So I think this is 2 C1 beta to the 2. 4, sorry, 4 C1 beta to the 2. Okay, and then we can conclude, okay. We have that for this value of n, okay, we know that f beta is larger than minus log 2 over n minus c beta and square root of log 8 over n. Okay, and well, this is something of the right order, right? Okay, so you see the optimal pi comes from if you want the optimal constant in here. If you want the optimal constant in here, okay, which is 1 over pi. Okay, so you need to put the optimal constant here. You need then okay, you need to take away the 2 here, which is bad. Because I mean, if you can replace here 2 by 1 plus epsilon. Because here you just need to say that things need to be smaller than 1. Okay, you don't need this thing to be smaller than 1/2. You just need this thing to be smaller than 1 minus delta. And you will get something large here, but it doesn't really matter. Okay, and most importantly, you need to get rid of the square root of n. Okay, because if not, you get a factor 2. Okay, this is the hardest part. Okay, but basically, this lower bound is still much. I mean, it's a bit of work, but it's not too difficult to get the optimal thing. Okay, so this is 1/2 of what I wanted today. Wanted to do today. Any question? Sorry?
You found a bound for some values of n, but that beta is the infimum over all n. I'm not exactly sure how you...
If you take the infimum over all n for?
Yeah, so that couldn't be like for bigger values of n.
No, but perhaps I write things in the opposite direction. Where did I put the infimum?
F beta, no? It's the infimum over all values. The log of Wn over n. Beta is the infimum over all n, right?
But this is perhaps a mistake. Is it really the infimum? It might be the supremum, right? Our thing is super additive, so it's a supremum. I wrote infimum, but it's a supremum. Yeah. You just need one value. That's the point.
Yeah.
Okay, let's think about it, but. Yeah, what you have is that for all n, f beta is larger than 1 over n e log wn. Okay, so of course, this cannot be equal to the infimum. This is equal to the supremum. Yeah. Very good question. Yeah, I think the other inequalities are in the right direction. Okay, so now there is a second thing I wanted to say is about basically some open problem for which, okay, it's basically giving you some partial answer to something, and well, this is something that people have known for 20 years, and basically nobody really knows how to go much further. So let's get back to the origin of the question. So we have shown that when you have very strong disorder, okay, when the free energy is negative, then if you take two replicas, okay, two polymers with positive probabilities, they will share the same endpoint. Okay, but when you talk about localization, you really would like localization for the full trajectory, not just for the endpoint. So what you would like to say is that when you take two replicas, okay, they actually, okay, let me take them with, they actually spend a lot of time together, okay, not only at the endpoint. Okay, so perhaps there could be several favorite corridors, but at least with positive probability, they should overlap. So the right quantity you want to look at is really this Ln x1, x2, which is just the quantity of overlap between your two paths. Okay, and so what you can be interested in is really the expectation under the polymer measure. So under two copies under of the polymer measure of Ln. Okay, and yeah, it's okay. This thing is not necessarily concentrated around its mean under this measure, but if you take this expectation, like taking the expectation here, okay, for some heuristic reason, it shouldn't make a big difference. So you would like to say that this thing, okay, is of order n if f beta is negative. Okay, and so there is a result going in that direction, and we are going to prove it now. But it is something very frustrating. So first, for this result, I'm going to assume that omega is Gaussian, and this time I'm going to use Gaussianity in quite a strong way. Okay, like basically I'm not, okay, it's not completely specific to Gaussian. You can make this result survive if you consider Poisson variable, okay? But basically you need this thing that your variable can be written as a sum of IID copies of itself, okay, of infinitely many, an arbitrary way, arbitrary many copies of itself. Okay, so, and okay, what's the theorem? So this is due to Carmona and Hu in 2002. And okay, so let me write two things. So first, A, well, the expectation of the expectation this thing, it's, okay, so omega standard Gaussian, IID standard Gaussians. And yeah, this thing is equal to 1 over beta times the derivative in beta of the expectation of log Wn. Okay, and B, which is an immediate consequence of A, it is that, well, the at differentiability points of f, the limit when n goes to infinity of 1 over n e okay, I forgot about the product here. Ln is equal to minus f prime of beta, and here I have a minus. Here I have a minus. This thing is decreasing in beta, so yeah. Okay, so yeah, the most important thing here is to prove A, B is completely standard. Let me just comment a bit on this, because B is due to convexity. We are going to prove it, but and the functions we are considering, they are not convex. So perhaps you might wonder where things come from. So so the important thing here, okay, is that so this, well, if you take the log partition function and therefore its expectation, this is convex in beta. If you take it non-renormalized. Okay, the reason is simply that Zn is the expectation of exponential beta times something. So, well, exponential beta times something, it's a convex function. It's a log convex function. The log is convex. And the expectation of a log convex function is log convex. Okay, and this is just Hölder. Okay? I'm just going to do it again. But it's just like you take Zn alpha beta 1 plus 1 minus alpha beta 2. Okay, it is smaller. Okay, just using Cauchy-Schwarz and the expectation of exponential beta 1 alpha exponential beta 2 1 minus alpha. Okay, I'm just using Hölder with exponents 1 over alpha and 1 over 1 minus alpha. So this is just Zn beta 1 to the alpha, Zn beta 2 to the alpha. Okay, this is basically the same proof as when we showed that lambda beta is convex. Okay, so this is not convex, but yeah, up to the addition of a function, of a fixed function, it's known. So this thing basically, it comes to the fact that for convex functions, you can interchange derivative and limits in a certain sense. Okay, so you're taking the limit of this, okay, and then you get this. Beta was missing clearly. Okay, so the limit of this has to be this. Okay, no, you're dividing by n. Okay, you're taking the limit on both sides. Okay, and part of the statement here is that this limit exists. Okay, and also because this function is convex, it is differentiable at every point except countably many. So this is also the case of this. Okay, so this assumption is not a big one. Okay, for most betas, it's true. Okay, so now let's. Okay, we are going to prove this, but perhaps we should first comment a bit on the results. So what are the open questions? Open questions. Prove that f beta negative implies that f prime beta is negative. Okay, I'm writing this implication. The other implication is true. Okay, you have to work a little bit to show that it's true at the critical point, but it's trivially true outside of the critical point. Okay, but yeah, this is an open question. It's not completely obvious even that f beta has no flat parts in the strong disorder regime. Okay. Okay, this has to be true, but I wouldn't know how to prove. And the second thing is prove that, well, f beta implies 1 over n ln beta omega. Oh, okay. Well, okay. The limit of this when omega non-Gaussian. Okay, the two things are widely open, basically. The only thing you can prove for relatively cheap is that in the Gaussian case, this has to be true for beta large. Okay, so there is a beta, but which is probably, which can be, we cannot exclude that it's larger than beta critical, which is such that for all beta large, this is true. Okay, and this is basically just by using some convexity. Using some convexity and some asymptotic, you can prove for f beta. Is the result clear? Okay, what you can show basically is that f prime beta over beta tends to 1. Okay, so that this thing, when beta goes to infinity, it has to tend to 1. This thing, when beta goes to infinity, it has to tend to 1. So for beta very large, basically, this localization property holds in a very strong sense. Okay, so let's go and let's prove this. And yeah, we are going to start with this part, okay, and try to see how from this we can obtain this. Okay, so yeah, what's the derivative in beta of the expectation of log Wn? Well, it's well, first I can take this inside because everything is sufficiently regular. I'm not worrying about anything here. And okay, so you have to check domination assumption if you want to do this, but they are satisfied with some large margin. So and then I'm taking the derivation of the log. So this is d beta log Wn beta divided by Wn. Okay, so this gives me two terms, basically. So when I'm looking at d beta of Wn, what I get is, well, first when I have beta omega and beta square over 2. So the beta omega gives me, well, this sum from n1 to n omega n xn is going to go down. Okay, and the beta square over 2 is also going to go down. So I get this. Okay, so here, okay, this second term is just going to give me a minus beta. I don't care about it. What's more tricky to analyze is what these terms gives. And I'm going to okay, so what you get here is, okay, minus beta n, okay? And before you get the expectation, and okay, you have this thing divided by omega n, so this is just an expectation under the polymer measure. Okay, so I get E n beta omega. And here, okay, let me write the sum here. Here I get this, E n beta omega. And here I get omega n xn. And okay. Okay, and here I get minus beta n. I want to rewrite this in a more, okay, what I don't really like is that I have this xn here. So, well, I want to make it disappear, so I can just write it this way, and this way. Okay, so what I have here, okay, is just the expectation of Wn omega nx times the probability that xn is equal to x. Okay, I have a sum of the terms. I'm just going to compute to look at these terms individually. Okay, and now what I will be doing is, well, to use a trick, which is Gaussian integration by part. Okay, it's just integration by part, but with a fancy name. So let me write this as a lemma. So lemma, if Z is a standard Gaussian and phi is a function with a convex function. Satisfying. Okay, so I think if I write this, I'm really safe. So max phi of u, phi prime of u is smaller than exponential u squared over 4. Okay, then the expectation of z phi z it's equal to the expectation of phi prime of z. Okay, so basically here, well, this is somehow a function of omega and x. Okay, this is going to be our phi. Did I say? C1 function. No need for convexity here. This is a C1 function of omega and x. It's sufficiently regular; you don't have to worry. So you can do this. Okay, and what's the proof of that? Well, I'm just writing the thing. So on one hand, here I have the integral of u exponential minus u squared over 2 times phi of u. Okay, I have 1 over square root of 2 pi in front, but I don't need to worry about it because this is going to appear there as well. So now what I can do is just integrate by parts. So here I will take I will integrate this and differentiate this. So if I do this, okay, this is this gives me minus exponential minus u squared over 2 if I integrate it. But I get the minus from the integration by parts. So this is exponential u squared over 2 minus u squared over 2. Here phi prime of u du, and yes, I guess this is a plus right here. Okay. So this term is 0. So this. Here you have phi u u exponential minus u squared over 2. Okay, so I don't really remember if I truly need this assumption here, but I guess it's better for this to be integrable. Perhaps it follows from the, okay. But at least, yeah, and you need an assumption on phi to make sure that this. Okay, you need slightly more than being integrable against. You need slightly more than this being defined. Okay, on phi. Okay, and so this is okay. And if you want to prove it rigorously, basically, you put some m here and there, and you make m tend to infinity. Okay. So now let's use it here, okay? And now the question is, what is the derivative of this with respect to omega and x, okay, for n and x fixed. Okay, so we have that expectation of omega x, e and p and beta omega xn is equal to x. This is equal to the expectation of g omega x and beta omega xn equal x. Okay, so okay, we can do that. So this thing here is a ratio. So I'm taking. So I just need to differentiate two things. So. Okay, so first thing, okay, so this is something divided by W and beta omega. Okay, when I'm differentiating the numerator, you see that here I have an exponential, okay, and in this exponential somehow, because I have the indicator xn equal x, omega and x always appears. Okay, so I get really the expectation of, so beta goes down. And then I get, exponential sum of n equal 1 to n, beta omega n xn minus beta square over 2. Indicator xn equal x. Okay? And then I have a second term, which is, okay, I get a minus in front, and I get, well, I get E n beta omega xn equal x. So here, okay, I'm just taking the numerator, the denominator. The denominator is going to get squared. So I have 1 over W and beta. Okay, it's squared. I'm just taking one of the copies there. Okay, and then I have here the derivative of this with respect to omega and beta that comes to there. When I take the derivative, well, somehow only the trajectories that go through x count. Okay, because if not, omega n x does not appear here, so it can be considered as a constant. So what I get here is exactly the same thing. Beta minus beta squared over 2, indicator x is equal to x. Okay, so after all, what I get is something quite compact expression. I get, okay, let me write it here. I get that this is equal to, well, this is nothing more than beta E and beta omega Okay, this was a P, right? So this is, I get beta everywhere, okay, and I get beta times the exponential of E n beta x xn equal x minus p n beta x xn equal x squared. Okay? Because this is nothing more than this, and this is this. Okay, except that I have this beta. Okay, so now I can take the sum over over x. If I take the sum over x, you can see that this first term here gives me exactly 1. Okay, because xn has to be somewhere. Okay, so this term here is going to cancel with that one, okay, because then I have n terms. And I have only the second one remaining, okay, and what I obtain is that d beta of exponential log wn, when this is equal to, okay, so I have this minus, I have the expectation, I have a beta, and I have the sum over n equal 1 to n, the sum over x in zd, and then the probability and beta omega xn equal x squared. Okay, and you can check that this is exactly what we wanted. Minus beta times the expectation of ln of e beta e and beta omega at n. All good? Okay, if you sum over x, this is just the probability that xn1 is equal to xn2 under the product measure. Okay, so something true for kind of a mysterious reason. Okay, this kind of computation, because there is another way you can see this, but I'm not sure you're going to like it. You can also get this directly using Ito formula. Okay, you can say that, well, basically beta times omega is just a Brownian motion at times beta square. Okay, and so this allows you to use Ito formula when you compute the derivative. Yeah, this thing is the Ito term somehow that you get. Sorry? No, the Brownian motion is the environment in that case. You're just saying that omega and x, this thing, okay, you say that it's the same thing as taking b and x at times beta square. Okay, so you're using the beta as your parameter for the Brownian motion. This is just because this is a Gaussian. Okay? Okay, so then you can say, okay, my log wn beta, it's a martingale with respect to my Brownian filtration. in time here. So I can use Ito formula for this, and yeah, this gives you some expression for this, and then when you take the expectation, basically the martingale term disappears, and this is the Ito term that you get. Okay, and this is the way it's done in Carmonahu's paper. Okay, so let me finally justify this. I don't know if you know about this. It's a bit like Paley-Zygmund. I think this should be something classical, but I've never seen it, this thing about convexity and differentiation outside of a statistical mechanics class. So, any question on the proof? Last thing is proposition. If phi n is a sequence of convex functions and limit when n goes to infinity of phi n of u is equal to phi of u for all u in R, then at all points where phi is differentiable, you have that the lim when n goes to infinity of phi n u plus is equal to the limit when n goes to infinity of phi n prime u minus, which is equal to phi prime of u. Okay, what is phi prime n u plus? It's a derivative on the right of phi prime. Because here I'm not assuming that phi n is differentiable at u. Okay, so okay, in our case, everything is okay. The function we are considering is really 1 over n log wn, the expectation of 1 over n log wn. This thing is differentiable at every point, but the important thing to remember in the theorem is that what's important for the thing to hold is not the differentiability of phi n, it's really the differentiability of phi. Okay? Differentiability of phi is required, and if it's not true, this is not going to be true. If phi n is differentiable for all n, basically, even if phi n is not differentiable for any n, this thing will still hold. Okay, you still have conversions to it. Okay, and yeah, the proof is basically one line. So, and perhaps in order to get the proof, it's better to think about the statement, the more general statement where you don't have this assumption. So, what you really want to prove is that the lim sup of phi n u plus is smaller than phi u plus, and that the limit inf of phi n u minus is smaller than phi. Okay, I put in prime u minus. Okay, and of course, the limit is larger. Okay, so if these two things are equal, then okay, these two things have to be equal, and because they are already ordered, and then you can conclude. Okay. This implies so that basically, yeah, you get that if phi prime u exists, okay, you already know that this has to be larger than this, okay, just because you have this inequality by convexity for every. So this implies that lim inf of phi prime u minus is equal to lim sup of phi prime n u plus is equal to phi prime u. Okay, and now if you take the lim sup of this, well, this is bounded by that. And if you take the lim inf of this is bounded from below by that. So. Okay, and now here, okay, you have two things to prove, but really B is A for the symmetrized function. Okay, so you just have to care about A, okay, because phi tilde is obviously convex. Okay, and okay, now you just know. Okay, so what you have is that phi n u plus. You know that this is always smaller than phi u plus epsilon minus phi u. Okay, this is just by convexity. Okay, so then you can take the lim sup on both sides. Well, this is smaller than, okay, now this converges by assumption, so you get phi u plus epsilon minus phi u divided by epsilon. And this is true for arbitrary epsilon, so you can make epsilon tends to 0, okay. And when epsilon goes to 0, this goes to phi u plus. Okay, and something that I haven't done, I mean, when you want to know, to see why this is true, basically, you can make a picture, try to make these things violated, and you see that you will need to make curves to cross at the wrong. Okay, so you can have a geometric intuition of why this holds. Okay. Okay, so this sums what I wanted to say about what I wanted to prove, at least for directed polymers on ZD. Maybe I can make a few comments on, okay, so first, do you have questions about the topic? So I can make a few comments about things that we didn't talk about. Yeah, what we said is that when you're in the weak disorder phase, trajectories, the distribution of the trajectories rescaled by square root of n converges to Brownian motion. Now you might want a similar statement in the strong disorder case. So the first question should be, well, by what should you rescale to get something non-trivial? So Okay, the conjecture is that if f beta is negative, then typically xn is of order n to the psi under p n beta omega, and psi is strictly larger than 1/2. Okay, and so basically you're in the very strong disorder phase. So favorite paths are really almost completely determined by the environment. Okay, you don't really want to take the best path or something in the neighborhood of the best path, but somehow, yeah, you want to find the best corridor around which you want to wiggle in them. And this best corridor, it's not going to behave like a simple random walk. Okay, the idea is that yeah, you want, okay, the random walk will have to pay some entropic price, okay, to see something further away, but it will benefit from it by seeing better environments. Okay, so the thing is that psi does not depend on beta, okay, in beta c infinity, but it does depend on d. Okay, so things are known about this, but okay. So before telling you what things are known, perhaps let me give you another conjecture, which is that if you look at the variance of log Wn, okay. Well, if you're in the weak disorder, okay, log Wn is of constant order. I mean, log Wn converges to something. So the distribution of log Wn is tight. Okay, so the fluctuations of this, they are of order 1, so the variance should be of order 1. But when you're, okay, so if beta larger than beta c, this thing is believed to behave like n to the I would say it's 2 chi, okay, in the sense that the typical fluctuation of Wn around its means should be of order n to the chi, and it's believed, okay, that 2 psi minus 1 is equal to chi, okay, for all d. Okay, what's the rationale for this? Basically, for a random walk going to a distance n to the psi, it has cost exponential n minus, okay, n to the 2 psi minus 1. This is roughly the probability that you go up to n to the psi if psi is larger than 1/2. This is just this large deviation estimate. And basically, by exploring a new box, okay, well, because this thing has fluctuation of order n to the chi, you might get something which is n to the power chi better than what you had before. Okay, so therefore, to make the incentive strong enough, basically, so this is the penalty, okay, the entropic penalty for doing this. This is the cost, okay, if you want. And the benefit should be, well, okay, if what happened in this box is better than this is by an amount n to the chi, okay, because basically you have two independent environments, okay. And the true fluctuation exponent is the one for when things balance out. So this is the reason why you should have this. Okay, simple heuristic, but somehow this is still an open conjecture. Okay, there is a paper which says that solves this conjecture for last passage percolation, but somehow it proves this and this, but for the two inequalities it has different definitions. So, I don't know. You make your opinion about it. It's a very good paper, okay, but I think perhaps you would like these to hold with the same definition for the two inequalities. Okay, so this is one thing completely open to show either this and this is, okay, not completely open, but still widely open. Another thing which is specific to dimension. So then having the value of psi is perhaps hopeless because it has no reason to be rational or anything, except in dimension 1, okay, where psi is equal to 2/3, exactly. Okay, and chi is equal to 1/3. So these things, okay, if you've seen talks about, well, anything related to KPZ, basically, you see these exponents pop up. And somehow these exponents, they are proved in some specific case. So if you want, you can take the polymer problem when beta goes to infinity. Okay, beta goes to infinity. I mean, it's infinity is larger than beta c, so. Okay, it's in the strong disorder regime, and basically it's the attractor. Okay, you believe that when you rescale things, what you see corresponds to the beta equal infinity picture. And for the beta equal infinity, there is a specific environment that you can consider. It's basically you consider exponential of omega to be an exponential variable. So omega is a log of an exponential variable. Okay, so in that case, what you see is oriented last passage percolation with exponential environment. And this has been known from the 2000 that basically you can compute things for this model, okay, using determinantal formulas, and you get these exponents popping up. Okay, so now the wide question is, can you prove things like with a flexible approach without using exact determinants? And yeah, I think even proving psi larger than 1/2 in that case is difficult in dimension 1. Okay, so what you can prove basically using a version of this argument is, yeah, if you take a polymer model which is based on a Gaussian random walk, for instance, or where your motion is a Brownian motion here, and then you make your environment IID in some sense. Yeah, then you can make things work. But if you really take simple random walk on Z, okay, and arbitrary environment, yeah, this is hard. Okay, it shouldn't be, but okay. And for Gaussian environment, basically, what people, okay, this argument here, okay, gives you psi larger than 3/5. So there are still room for progress. Okay, basically you get psi, which is between 3/5 and 3/4. Okay. Okay, using these kind of heuristics. Okay, so this is one thing, And the last thing you might wonder about is scaling limit for the model. So, okay, we have a model which, okay, so you can, so the question you might ask, okay, is that, is there a continuum version of the model, a true continuum version of the model? So, what's the continuum equivalent of random walk? Well, it's Brownian motion. Okay, what's the analog of IID environment? Well, this is Gaussian space-time white noise. Okay, so this is just what you get by, okay, you take your environment, you integrate it against test function, you look at the limits. Okay, if you look at the weak form of the limits, you will get a random distribution. Okay, so what you can try to do is, well, say that, well, you have a, say, the Wiener measure, okay, and you have a white noise, and you want this to be proportional to exponential, the integral, okay, I should put some t here and some beta here. 0 to t, beta, and here, okay, I get somehow okay, ht, okay, and this is the W integrated against the graph of B. Okay, so you have your Gaussian white noise, and you want to integrate it against basically. Okay, so you know, Gaussian white noise, it's something you give a set to it, and it spits you a Gaussian. Okay, and for disjoint sets, it gives you independent Gaussians. Okay, and the variance of the Gaussian is basically the size of the set. Okay, so another way to see it is you say, okay, to my Gaussian white noise, I give it an L2 function. Okay, and it spits me a Gaussian. And basically, this is a Gaussian process, and the covariance of the process is given by the scalar product in L2. Okay, and here I'm integrating against something which is not a set. Okay, it's not the indicator of the graph because it's not I would get 0. It's really the integral from 0 to t of the Dirac mass at t bt. Okay, and this thing is really not in L2. Okay, so this thing, okay, it's really not well defined. Okay, it's a very big Gaussian. But again, then because you're integrating against Brownian motion, you might hope for things to average out. Okay, if you're just taking away the variance. In dimension 1, somehow, even though it seems a very complicated object, it's not that difficult to show that this thing exists. And the thing is that if you take, okay, beta, which is n to the minus 1/4. Okay, so remember, earlier we had n equal 1 over beta to the 4th in dimension 1. So this is exactly the same thing. This is the threshold at which the variance starts to grow. Okay, so beta n is equal to this. Basically, your discrete model is going to tend to this continuous model. Okay, you have so this is something which is established, and we didn't have room to talk about. And basically, for the limiting model, these things are known. Okay, so in dimension 3 and more, this thing has absolutely no chance to work. In dimension 2, these things doesn't make sense, but just by a little bit. So yeah, it turns out that if you take beta n to be just proportional to this, okay, and here you can take beta somewhere, and it will give you the beta of this. Okay, here you have to take beta 0 very specifically. I think it's 1 over square root of pi or some constant. And okay, and then you can take. I don't remember. There is a second term here, which I don't remember if it's log n or log n to the 3 half. But yeah, okay, if you take beta n like this, then you get a range of continuous models. But they are of a different nature than this one in the sense that they are not models that are a function of a white noise somehow. Like this thing exactly doesn't make sense in dimension 2, but you can still get scaling limit, and this is super recent work. This has been done during the pandemic, basically. I mean, people have thought about it. There was some preliminary work before, but like, okay, there have been basically 2 decades of exploration on what the scaling limit in dimension 1 is, okay? In dimension 2, this is very recent, and it's still quite a mysterious object. Okay, and basically in dimension 3, if you want to get a scaling limit, yeah, you should get very close to the critical point. Okay, and yeah, because it's difficult to, it's hopeless to know what beta c is. It's tricky to imagine what it should be. But yeah, I guess if you place yourself near criticality, okay, if you take beta c plus epsilon and you make this epsilon depends on n, you might get a scaling limit, but this seems very challenging, so perhaps not a good direction to look for. Okay, so yeah, next week, polymer on the tree for which we can compute things, and we'll see the connection with branching random walk on Z. Okay.